Hi, Bhaskar this side. We know that methanol and acetonitrile is widely used as a organic solvent while preparing mobile phase for reverse phase chromatography. But let us understand why someone use methanol and why another use ACN while preparing the mobile phase. Are there any differences between these two very important organic solvent? Yes. There are certain differences, and that is the purpose of making this video. Now, this particular presentation is also influenced because of the article published by Simadju. The name of the article is 7 key differences in the use of methanol and acetonitrile. So, the credit also goes to this article. So, what are the properties of ACN and methanol? So, you will see the structure of ACN and methanol onto the screen. So ACN is a polar aprotic acid. It brings the pi-pi interaction because of the presence of C triple bond N. It also can form the hydrogen bonding with the another molecule because of the presence of highly electronegative atom like nitrogen. Now when it comes to methanol, methanol is a polar protic acid and it can interact with the another molecule with the formation of hydrogen bonding. Now, why the hydrogen bonding is possible? Because on methanol, there is a presence of OH or the hydroxy group. So, oxygen is highly electronegative atom and it can partially polarize the molecule. It will generate the slightly negative charge onto the oxygen and slightly positive charge onto the hydrogen atom. So this hydrogen atom, which is slightly positive charged, can form the hydrogen bond with the atom having a slightly negative charge. So let us understand what is meant by polar protic solvent or polar aprotic solvent. And here is the definition onto the screen. So what is a polar protic solvent? So polar protic solvent is a solvent that has a hydrogen atom bound to an oxygen. For example, as in case of hydroxyl group, or bound to a nitrogen. For example, as in case of amine group, or bound to a fluorine, such as in case of hydrogen fluoride. So you can very clearly see that there is hydrogen atoms present into the ACN, but these hydrogen atoms do not form any bond with the nitrogen. And hence, we cannot say ACN is a protic polar solvent. But when it comes to methanol, you can clearly see that the hydrogen forms a bond with the oxygen, and hence methanol becomes polar protic solvent. When it comes to usage of these organic solvents for preparation of mobile phase, and where we are selected UV as your detector, then the UV cutoff is very important for all given organic solvent. The benefit of using ACN over methanol is it has very low UV cutoff, like 190 nanometer. But in case of methanol, it has a UV cutoff value of around 210 nanometer. Now what this indicates? This indicates that the ACN can be used even to make the measurement at 190 nanometer wavelength. But methanol may not use, methanol can be used only for detection of having a wavelength more than 210 nanometer. Otherwise, you will get lot of noise in case of using methanol as a part of your mobile phase, having a detection wavelength less than 210 nanometer. The another important factor is the cost of methanol and ACN. Here, the ACN is costlier than the methanol. So whenever there is a possibility of using methanol over ACN, you must prefer methanol to save cost to your laboratory. The second important factor is the column pressure. See, our HPLC systems are built to withstand until certain back pressure of, let us say, around 4000 psi. And beyond that, your pump will not work. So, a system or the mobile phase which creates minimum back pressure must be of the preference. Now, what is the relationship between organic solvent and the column back pressure? Now, here I have compared the back pressure of ACN with the water as a mixture. Similarly, methanol with the water as the mixture. So what is, if you look at the diagram onto the screen, you will find that there is a water organic solvent 1:1 across the x-axis, and the pressure is measured across the y-axis in the unit of psi. The column used during this experiment is the ODS 150 mm 4.6 mmID 5 micrometer, 5 micron diameter, and the flow rate is 1 ml per minute. So if you look at the water ACN ratio and their pressure, you will find that the back pressure is much lower with the mixture containing ACN. You will also see that the back pressure with the higher temperature like 40 degrees Celsius is much lower as compared to the back pressure generated by the same system at the lower temperature like 25 degrees Celsius. So in case if you are struggling with the back pressure and if you are using methanol as your organic solvent, then it's a good point to replace methanol by ACN, and you will find drastic change in the, or you can find the drop in column pressure. Giving the temperature to your column can also help you in minimizing the column back pressure. Let us understand now the strength of these two important organic solvent. Comparison of elution strength of methanol and ACN. Now this is the nomogram of solvent strength for reverse phase chromatography. If you look at the initial phase of the strength, I have just draw a one green line for 10 part of ACN as to water. If you see that it actually matches with the 15 part of ACN, 15 part of methanol water. Now what this indicates? This indicates that with the smaller proportion of organic solvent and water, ACN gives the higher strength to the mobile phase. That means ACN makes the mobile phase more stronger as compared to the similar proportion of methanol. But when you move towards the higher proportion of organic solvents, at the end you will find that there is no much difference found between the mobile phase strength prepared with methanol or acetonitrile. So let me show you with the example of how the retention time gets changed because of the change in the methanol or ACN. Now the top chromatogram, which is in the red color, is with the water methanol 4060, and the chromatogram with the color of orange is with the water ACN 4060. So the proportionate of water and organic solvent is same in both the experiment. Now there are 6 different analytes: methyl paraben to ethyl paraben, then isopropyl paraben, N-propyl paraben, isobutyl paraben, and last one is N-butyl paraben. So if you look at the elution time of these parabens in methanol, you will find that they actually gets retained for good amount of time. But when it comes to ACN, you will find the retention time is much reduced. Now, this one experiment proves that the ACN is more stronger than the methanol when it comes to reverse phase chromatography. Now, the next important question could be why methyl paraben elutes first and N-butyl paraben elutes last. Now, look at the structure of methyl paraben and butyl paraben. You will understand that the carbon chain length is short in case of methyl paraben, whereas the length of the carbon chain in butyl paraben is longer. Now, what it means? What happens in case of the change in the carbon chain length? The compound with the shorter carbon chain are less non-polar. The compound with the higher carbon chain are highly non-polar. So, in this case, you can clearly see that the N-butyl paraben is non-polar as compared to methyl paraben. Now, what is the column we are using? We are using ODS column, SIMPAC VP ODS or C18 column. And the C18 column, retention onto the C18 column gets governed due to the hydrophobic or non-polar interaction. The compounds which are non-polar are going to interact or retain for longer time onto the C18 stationary phase. And in this case, as the butyl paraben has the higher non-polarity nature, it is going to retain for longer time onto the C18 stationary phase. The next important point is different in elution selectivity between methanol and ACN. And I am going to explain this different selectivity based on to elution of phenol, benzoic acid and para-toluic acid. The mobile phase used for methanol is buffer methanol 4060 volume by volume, and for ACN it is buffer ACN 6040 volume by volume. The column used is SIMPAC VPODS. So in this case, you will find that with the methanol, the elution order is phenol elutes first, then benzoic acid, and then the para-toluic acid. But in case of ACN, you will find that the benzoic acid elutes first, then phenol, and then at the end para-toluic acid. So why is the reason for faster elution of for benzoic acid with ACN? What makes to elute benzoic acid first or before phenol? So in this case, you must understand that there is a additional interaction with the ACN of the benzoic acid, and that is the pi-pi interaction with the pi electrons present onto the carbonyl oxygen and the C triple bond N of acetonitrile. Now, does this pi-pi interaction possible with the methanol? Because methanol does not contain pi electron, and hence this pi-pi interaction is not possible with the methanol, but it is quite possible with the ACN. And because of this extra interaction, this benzoic acid is going to prefer ACN, which is present into the mobile phase, and hence it will come along with the mobile phase and hence elute first and faster. Now, why paratoluic acid is retained for longer time then? As we discussed in the last slide, the presence of alkyl chain brings the hydrophobicity into the molecule. And if the hydrophobicity is available, then the interaction with the C18 stationary phase can happen because of the hydrophobic interaction. Now in phenol, benzoic acid, there is no presence of alkyl chain. But in case of para-toluic acid, you have a methyl chain. Now this methyl chain brings the little hydrophobicity, and because of that there will be a good amount of interaction with the hydrophobic stationary phase like C18, and this results into the good amount of interaction with the stationary phase for para-toluic acid, and hence it retained for longer time. Now let us understand the precipitation of the buffer while mixing with the ACN and methanol. See, for reverse phase chromatography, in case if you want to maintain the pH of your mobile phase, you need to add certain buffer salts. But the challenge here is, now what is the allowable concentration of your organic solvent? And it's purely depend on to the precipitation of buffer salt. Buffer salt start precipitating while there is a higher proportion of organic solvent. So in case of ACN, what is the highest amount of ACN can be added with the different salt solutions? You can see onto the screen. Now where there is a big circle that indicates that there is no precipitation happening. So let me explain you with the help of sodium phosphate buffer having the pH of around 2.6. Now in this presentation, there are 5 different concentration of the buffer salt used. The first one is with 5 millimolar per liter. Second is with 10 millimolar per liter, 20 millimolar per liter, 50 millimolar per liter, and last one is with the 100 millimole per liter. So with the 5 millimole per liter solution of sodium phosphate buffer, you can use 100% ACN. That means there is no need of water to solubilize sodium phosphate buffer having the concentration of 5 millimole per liter. But when it comes to 10 millimole per liter concentration, you will see a precipitation beyond 95% of ACN. Similarly, with 20 millimole per liter of sodium phosphate buffer solution, you will start seeing a precipitation with 80 part of ACN, and obviously the 20 part will be your buffer salt containing, let us say in this case, of 20 millimole. Similarly, in case if you are preparing a 50 millimole per liter concentration of sodium phosphate buffer, the precipitation of salt will happen with 80 part of ACN and 20 part of buffer. Similarly, with 100 millimole per liter of sodium phosphate buffer solution, precipitation happen at 75 part of ACN and 25 part of buffer. In case of sodium phosphate buffer, approximately pH 6.8, this ACN is not at all a good organic solvent. In case of sodium citrate buffer having pH approximately 3.1, no precipitation happens with 5 mole, 10 mole, 20 mole and 50 moles per millimoles per liter of salt, and with 100 millimoles per liter of sodium citrate buffer, you can still use 95 part of ACN and 5 part of your buffer. In case of ammonium formate buffer with 3.7, 6.4, 4.7 and pH 6.8, no precipitation happens with the ACN. So ACN can become the preferred choice in case of you are using ammonium formate buffer. In case of methanol, you will find that no precipitation of salt is happening in case of methanol in majority of the cases. And hence, you can make a conclusion that methanol is a good organic solvent as per as precipitation of salt is concerned. Now let us understand the heat of reaction from mixing with water. So when you mix methanol with water, what is the heat of reaction? Or when in case of your mixing ACN with water, what is the heat of reaction? So when mixed with water, Methanol reacts exothermically, and you must have seen the increase in the temperature of the solution prepared. In case of ACN, it is an endothermic reaction, and you will find the drop of the temperature of the solution prepared. As the ACN mixture gradually returns to room temperature, bubbles tend to form in the liquid, so that there is a strong need of good amount of sonication. Methanol produces heat when mixed with water, which has a degassing effect. Finally, preparing a water and methanol mixture as the mobile phase requires less care than in the case of acetonitrile. I hope you now must have understood what is the challenges, the differences between using methanol and ACN while preparing the mobile phase. Thank you very much for watching this video, and I will meet you soon with such kind of very useful and informative content. Bye bye.